Next topic is about, in essence, continuous random variable. So normal probability distribution, starting with the standard normal distribution. Standard normal distribution.
If a continuous random variable has a distribution with a graph that is symmetric and bell-shaped, we say that it has a normal distribution.
Key concept: the standard normal distribution is a specific normal distribution having the following three properties. 1. Bell-shaped. The graph of the standard normal distribution is bell-shaped. 2. Mu is equal to 0. The standard normal distribution has a mean equal to 0. 3. Sigma is equal to 1. The standard normal distribution has a standard deviation equal to 1. In this section, we developed the skill to find areas or probabilities or relative frequencies corresponding to various regions under the graph of the standard normal distribution. In addition, we find z-scores that correspond to areas under the graph. For a continuous random variable, the probability of a single value of x is always 0.
Normal distribution, we really have to pay attention to those three. If you're claiming something is a normal distribution, you have to come up with parameters mu and sigma. Okay? And it happened to be, mu happened to be 0 for SND, standard normal distribution. And sigma happened to be 1 for SND. And this is what is used for the concept of Z-score, if you will. So a Z-score of 0 means the number is equal to the average. Concept is extremely important. It doesn't mean that horrible. On the other hand, if it's negative, it means below average. The thing that I want to add, and this is important, any continuous random variable, when that happens, the probability of a single value is always 0 because it doesn't cover any area. Now, if you look at the formula at the top right, it gives the mathematical equation for the normal distribution. Y is equal to e to the power of minus, parentheses x minus mu quantity squared over 2 sigma squared, and the whole thing over sigma square root of 2 pi. Sometimes they write it as y equals 1 over sigma square root of 2 pi e to the power of minus x minus mu squared over 2 sigma squared. This is the equation for this curve, for this function. And this function, the total area under the curve represents the total probability, and therefore it's equal to 1. Of course, pi is a constant. Sigma and mu will be given to us, and that gives rise to the function that you can see. And when they want to calculate the probability, they have to calculate the area under the curve, which requires calculus. That's why you're given a table, or you can use a calculator or any other technology. But understand the concept is the area under the curve is calculated using calculus and the integral of a to b f of x dx. Just in case if anybody is familiar and comfortable with calculus, that's the concept. Now, that's a general curve. As you can see, it's bell-shaped. As you can see, it's symmetric, and it's symmetric about mu. Now, if this represents probability, the total area must be 1. If this represents probability and it's symmetric, on each side, the area must be 0.5. It is extremely important to understand this concept if you're interested in reading tables. You really need to know how this thing works. Again, the whole area is 1. Why is that? Because it represents the total probability. Because of the symmetry on each side, we have an area of 0.5. Now, when we look at these curves, remember the total area under the curve must be 1. Okay? So, for example, if you have the same means, mu1 is equal to mu2, smacked in the middle. If sigma is larger for one of them, in this case, sigma 1 is larger than sigma 2. For the blue one is sigma 1. So it spreads longer than the other curve. The other curve, they are closer to mu. Remember, the total area must be 1 and it doesn't change. In this case, we have different means, different standard deviations. So if you compare this to the very first one, in essence, you're looking at the same curves, but one has shifted to the right. because they don't have the same mean. That's the idea. The mean may be different, standard deviation may be different. In this example, if you see the shape is identical, it's just that the means happen to be at different points. So that's a concept that you want to pay attention to. All of it comes from the fact that the total area under the curve represents the total probability of 1. Normal distribution is bell-shaped, bell-shaped. The mean, median, and mode are equal and located at the center of the distribution. The normal distribution curve is unimodal. It has only one mode.
The curve is symmetrical about the mean, which is equivalent to saying that its shape is the same on both sides of a vertical line passing through the center. The curve is continuous, i.e. there are no gaps or holes.
The curve never touches the x-axis. Theoretically, no matter how far in either direction the curve extends, it never meets the x-axis, but it gets increasingly closer. The total area under the curve equals 1 or 100%.
Finally, the empirical rule that we discussed. And when we start from the mean, we go one standard deviation away on each side. It covers 68% of the data. 2 standard deviations away covers 95%. And 3 standard deviations away covers almost everything, which is 99.7%. That's important to see. That comes from this graph. And if you look up the table or if you use technology, you can easily see these numbers. In fact, that 95% is an approximation. It's 95.4%, just to give you an idea. Or that 68% is about 68.26%. All right, empirical rule, we had seen it before, nothing brand new. A uniform distribution is also a continuous one. So a continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. So it ends up being a rectangular shape. Properties of uniform distribution.
1. The area under the graph of a continuous probability distribution is equal to 1. 2. There is a correspondence between area and probability, so probabilities can be found by identifying the corresponding areas in the graph using this formula for the area of a rectangle. Area is equal to height times width.
The graph of any continuous probability distribution is called a density curve, and any density curve must satisfy the requirement that the total area under the curve is exactly 1.
Density curve, area is 1. So because the total area under any density curve is equal to 1, there is a correspondence between area and probability.
JFK Airport in New York City, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 5 minutes. All of the different possible waiting times are equally likely. Waiting times can be any value between 0 and 5 minutes. It's a continuous value. So it is possible to have a waiting time of 1.23456 minutes. Find the probability that a randomly selected passenger has a waiting time of at least 2 minutes.
When we look at this case, we can, by the way, do the drawing on our own. You basically have a horizontal axis. X represents the waiting time in minutes, and you have the vertical axis P of X. It's important to know that because it's going to go from 0 to 5, if the total area under the curve is 1, we can find the height, which represents the probability. So the very first thing we need to understand, the area is 1, and the width from 0 to 5 is 5. And so what is the height? The height would be the reciprocal of that. Why is that? Because the product of 2 numbers that are reciprocal would be 1. So the answer is the reciprocal. How do you find the reciprocal? Very simple, 1 over 5 or 0.2. That is the height. That is the probability, if you will, in general, which is a uniform case. So what is the probability of wait time that is at least 2 minutes? That means, so this is 2, and we want at least 2. That means larger than 2. Area under the curve represents the probability of interest. So probability of at least 2, probability of x larger than or equal to 2. We need to calculate the area, this simple case. The height is 0.2. From 2 to 5, that means 3. And there you have it. So the probability of at least waiting for 2 minutes is about 60%, according to this. So that's a uniform distribution. As it was mentioned before, standard normal distribution, we're going to use SND for short, has the following parameters. Mu is 0, sigma is 1, and when you ask an instructor whether they're going to curve the grade or not, you are referring to this curve Z-score. We discussed the Z-score as x minus mu over sigma. And to come up with the answer, we can use the Z table or we can use a technology. To the left of a Z value, we can look up a Z value in the table and use the area given. Now, the Z-score may be negative or positive. Again, I can't emphasize this enough. The Z-score is negative. Let's say a student has a Z-score of negative on their first exam. It doesn't mean the exam score is negative. It's just the exam score is below the average. Or a Z-score of 2. That means it's 2 standard deviations above the average. Now, to the right, look up the Z value and subtract the area from 1. Now, one of the things that happens when you want to look up a table, if you get comfortable with that and you remember the concept of a symmetry, this is really referring to the table here. The tables are different in different texts. In some texts, the tables go from 0 to infinity, and you have to adjust for it accordingly. Most of the texts nowadays, they have the Z table for negative values and the positive values. They have made it easy for the students. And by symmetry, the area to the left of a negative value of Z is the same as the area to the positive value of Z. And sometimes one may be easier than the other to look up. And I mentioned that has become a process in a moment. And if you want it to be between two values, such as this one, look at the graph. The graph is extremely important. So between two Z values, look up both Z values and subtract the corresponding areas. So that's how it's done. Let's look at a very simple example to get us started. We are trying to just get comfortable with reading tables.
A bone mineral density test can help identify the presence or likelihood of osteoporosis, which is measured as a Z-score, and the normal distribution. So mu is equal to 0 and sigma is equal to 1. Question: a randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density score less than 1.27.
So we want to see how this is done. So here's the graph. Notice mu equals 0 happens in the middle, 0.5 on the left, 0.5 on the right. And you look at Z equals 1.27. What I want to mention is that number 1.27, when you do the drawing, it may not be to scale. It doesn't matter. By looking at it, I hope you realize the answer must be larger than 0.5. Why is it important that you realize that? Because if you're looking up a table or you're using a calculator to get to the answer, and the answer is less than 0.5, you should recognize it can't be right. So how do we look up a table? Here's the portion of a table known as a Z table. So I want you to pay attention to the way we read that. If you look at a Z table, on the left column, you read the number which has 2 digits, 0.2 for example. So it has 1 decimal. The second decimal comes from the top row. So we want 1.27. How do we locate that? The left column gives us 1.2. The top row gives us 0.07. And the two result in the answer 0.8980. 0.8980. This is reading the table. I will discuss the calculator in a moment, but in general, we should be able to read the table. And this is a positive Z-score, by the way. And here's the interpretation. The probability that a randomly selected person has a bone density test result below 1.27 is about 89.8%. Okay, we'll conclude that 89.8% of people have bone density levels below 1.27. That was dealing with the table. Now this table, you can find it on Canvas. So this is the negative z-score. As you can see on the left side, you see the negative z-score. And at the top, you have the second decimal. And there are a couple of asterisks with the arrows. Let's just show the answer. Those are some common values. So if you look at the first one, reads negative 1.645. Take a look at the very first asterisk here. And if you go at top, you see 0.04 and 0.05. So it's between the two. That's why negative 1.645 gives you the area to the left as 0.0500. If you look at the second asterisk, okay, the top one, this one is between, look at the top, it's between 0.07 and 0.08. Everybody can see 0.07 and 0.08. It's between the two. So if you look at this asterisk, negative 2.575, that gives you 0.0050 to the left. Now, those are negative z-scores. And the next table, positive z-scores. Again, it's area to the left. Don't forget it's area to the left. Notice what happens. Let me just look at those two asterisks that was mentioned. Negative 1.645. Area to the left is 0.05. Negative 2.575. The area is 0.005. And by the way, don't mix up the area with z-scores can be negative or positive. And so when we look at positive z-scores, notice what happens. Look at those asterisks. We are changing the z-score to positive, 1.645. So area to the left is 0.95. Understand what happens. Area to the left is 0.95. So what is area to the right of 1.645? 1 minus that. This is 1.645. And the area to the left is 0.95, but the area to the right of this number, is the same as the area to the left of this number by symmetry. Now take a look at the area to the left of negative 2.575, 0.0050. 0.0050. Now to the right of positive 2.575 must be the same. Check this out. This one is what? To the left of it. If you subtract this number from 1, you get the same number, 0.005, area to the right of 2.575. So the idea is these two areas are the same. Just if this is the z-score, which is negative, for example, let's say z equals, let's make it up, minus 2.1, and this is the z-score of positive 2.1, the area to the left of z equals negative 2.1 is the same as the area to the right of z equals positive 2.1. So that is in case you need to read the table and get comfortable with it. We are looking at normal distribution, specifically SND, standard normal distribution, in which case mu is 0, sigma is 1. We've already mentioned the meaning of Z being between A and B. The probability of A is less than Z less than B denotes the probability that Z scores is in between A and B. And the rest is obvious. So we want to find the area to the left of Z equals 2.06. You should always start with the graph. And now you can look up a table. Those of you who have access to a table, see if you can find this, or maybe we go through that, then I will show you. Just I want to make sure that We are comfortable with that. So you go to the Z-score, which is positive Z-score, and you look for 2.06, and the number that gives you should be 0.9803. I'll show you with the table in a moment. The area to the right of negative 1.19. Again, you do the graph, and you can read the area to the left using the negative Z-score, the left of negative 1.19, and subtract it from 1. You can also read the area to the left of positive 1.19. That gives you the same answer, I believe. And so it ends up being 0.8830. So that's how you come up with the answer if you want to use the table. We'll go over that in a moment. And also technology, whatever technology you use is fine. For example, for a TI calculator, you use those in the order. Second, var stands for variables, normal CDF, and then you put 4 entries, the left bound, right bound, mean, standard deviation, you come up with the answer. Now, one of the things is important when you want to put the numbers. If you look at the very first one, for example, there is no left bound. So, and remember, it continues indefinitely on both sides. So really the left bound is minus infinity, if you will. However, if you pick a big number on the negative side, like minus 1,000, really will do the job. On the other hand, if you look at part B, it goes indefinitely on the right side. If you large number on the right side, it will do the job. And so 1,000 would be a good choice. You don't have to stick with 1,000. Just for the sake of argument, if you use 10,000, it works fine. If you use 900, it works fine, because generally speaking, within 3 standard deviations, we cover 99.7%. I want you to know that. So use a large number, it will do the job. Look at the lower point. The lower bound, I have used negative 1,000. And by the way, make sure you do not mix up the negative and a minus sign, 2 different things. And the upper is 2.06. And again, you can change the negative 1,000 to any number you want, as long as it's a very, very small number. On the left, minus 900 will do the job, minus 10,000 will do the job. Mu is 0, sigma is 1, paste it, and you have the answer here. I have 2 of them, parts A and B, at the bottom also. Let's see if we can do this using a table. So 2.06. So this is positive Z-score. So you're looking at 2.06. So 2.06. So everybody can see the 2.0 and then 0.06. And that is the bottom one, this one. 0.9803, reading it from the table. So that's 0.9803. Now we are looking at negative 1.19. Let me show you how we do that. 2 different ways. Negative 1.1 here, and then we are looking at 0.09, and the answer is 0.1170. So what you're really looking at is the area to the left of this number. So how do you arrive at the answer that you want? 1. So what we want is this area. So 1 minus this number. 1 minus 0.1170, which is 0.8830. Or look at the red area, look at the blue area. We want the blue area. This number was negative 1.19. Now, if you look at the area for the positive Z-score all the way to positive 1.19, in one shot you have the answer by symmetry. So let me go down and show you the positive Z-score. So let's go to positive Z-score. So we are looking at positive Z-score. So 1.1, 0.09, and right in front of it, this is the answer without having to subtract 1. Why is that? This represents the following. The area to the left of positive Z-score of 1.19. And so that's how you arrive at it if you want to use the table. It is faster to use the fact that they are symmetric, and therefore you go with positive 1.19, you can get to the answer. All right, let's do this as far as a calculator is concerned. So second var stands for the variables. Bring it down to number 2, normal CDF. Okay, lower. Now, -1, just put any number. That's good enough. But let's put minus. Let me change the number just on purpose. Okay, you see -1,000 here, class. Okay, you see -1,000. But on purpose, let's change it to 900. That's good too. So I'm looking at part A, Z is less than 2.06. So the upper is 2.06. Mu is 0. Sigma is 1. Enter, enter. And you get to the answer that we had here, by the way. Notice is 0.9803. And even if you use -900, makes no difference because, as I mentioned, within 3 standard deviations away, we cover just about everything. And for the next one, second was normal CDF. Again, we are using now for P is for the second one, the probability of Z larger than -1.19. So now the lower limit is -1.19. The upper limit, again, I'm going to change it on purpose. Again, just use 1,000, but let's just use 1,200. I hope you understand why I'm doing this. I'm doing this on purpose to let you know you want a fairly large number, and you get to the answer, 0.88297. And if you do the rounding, you come up with the same answer. All right, we're going to move on to the next example. I want to make sure that we are comfortable using tables and technology. First, graph. I can't emphasize this enough. The graph helps you have an idea what you're doing. So in essence, we are interested in the probability between the two values. And so with that being the case, all you have to do, look this up from the table by looking both numbers and subtract the area to the left of -1.37 from the area to the left of 1.68. I'm showing you the technology, how we use that. The next one, the area from 0 to 2.32, that's what we want. The area from -infinity to 2.32 is 0.9898. In other words, this represents this area. And then you subtract the left side, which is left side of the ZScore, which is 0.5. One other way that you can do this, dealing with the table. Look at this method. I'm going to put it up here. Now this area, this is number -2.32. This area is of interest to us because it's the same as the shaded region from 0 to 2.32. So you can read this area from the table of negative Z-scores subtracted from 0.5. I'm telling you various methods of handling this. So find the area to the left of -2.32 and then subtract it from 0.5. It gives you the same answer. I highly recommend you guys try this on your own so you get familiar with different ways of approaching the table. So here's the next one.
Using the same bone density test, normal distribution mu equals 0 and sigma equals 1, find A, the probability that a randomly selected person has a result above -1, which is considered to be in the normal range of bone density readings, and B, a bone density reading between -1 and -2.5 indicates the subject has osteopenia, which is some bone loss. Find the probability that a randomly selected subject has a reading between -1 and -2.5.
And the short for normal distribution. Part A is asking for P of Z larger than -1. I would draw something like this. Z equals -1, and you want the area to the right. Okay, this area. That's it. So do a drawing, doesn't have to be to scale, but it will help you see that even if I don't have the answer, I know for sure it's larger than 0.5. And that's the idea, because to the right of it is 0.5 and we have more. And so 1 minus 0.1587, and that's using the table or technology. It is absolutely up to you. So the probability of randomly selecting someone with a bone density reading above -1 is about 84.13%, which means 84.13% of people have bone density levels above -1. All right, so above -1 is considered normal, and 84 seem to have a normal bone density. The next one, between -2.5 and -1. So again, let me just quickly graph this for you. We're going to go from -2.5 to -1, and we are interested in this shaded region. That's the idea. You go read it from the table and subtract area to the left of -1 minus area to the left of -2.5. Interpretation. There's a probability of 0.1525 that a randomly selected subject has a bone density reading between -1 and -2.5, or 15.25% of people have osteopenia, weak bones. That's the idea. It's not the same as osteoporosis. Weak bones with bone density reading between the two numbers. Now, we're going to switch gears. We found the area. Fine. What if we want to go back? In other words, the area is given, and we want to find the z-score. So we want to look at the reverse process, if you will.
Draw a bell-shaped curve and identify the region under the curve that corresponds to the given probability. If that region is not a cumulative region from the left, work instead with a known region that is a cumulative region from the left. Use technology or the z-table. Find the z-score. With table A2, use the cumulative area from the left, locate the closest probability in the body of the table, and identify the corresponding z-score.
So in short, use the table or technology. Either way, you can find the answer.
Critical value. For the standard normal distribution, a critical value is a z-score on the borderline separating those z-scores that are significantly low or significantly high. Notation. The expression z sub alpha denotes the z-score with an area of alpha to its right.
Let's see what we mean by that. Find the value of z sub 0.025. This is a notation that subscript is known as alpha. That's the alpha in the expression. So first, I want to explain the meaning of that. Okay, so you're looking at this concept. The area to the right is 0.025. That's the meaning of this notation if it's given in this format. So first, the meaning of a notation.
The notation of z, and I can't remember how to say it, a 0.02.
Z sub.
Z sub 0.025 is used to represent the z-score with an area of 0.025 to its right. Note that the value of z equals 1.96 has an area of 0.025 to its right, so z sub 0.025 equals 1.96. Note that z sub 0.025 corresponds to a cumulative left area of 0.975. Caution, when finding a value of z sub for a particular value of, and then what do you say?
Alpha.
Alpha. Note that alpha is the area to the right of z sub alpha, but the table and some technologies give cumulative areas to the left of a given z-score. To find the value of z sub alpha, resolve that conflict by using the value of 1 minus alpha. For example, to find z sub 0.1, refer to the z-score with an area of 0.9 to its left.
The idea is understand what the question is asking and understand how the table works and understand how the technology works. That's the idea behind that. So for example, when you want to look, this one is, which is 0.025, you really need to understand this area all the way to the end is 1 minus 0.025, which is 0.975. And you need that so you understand how you come up with the answer. So to find the z-score, locate the cumulative area to the left in the table. So you have to locate 0.975 in the body of the table. The table you just looked up. In the body of the table, you look for 0.975. I'm going to go over that in a moment. And if you want to use a calculator, take a look at, again, the information at the bottom right. You use inverse norm, which means normal, and you put 3 entries. So see how it works. You put inverse norm. How do you find that? Again, second and variables. You put 3 entries, the left area, 0.975, mean and standard deviation, and it gives you those answers. By the way, by symmetry, if the area to the right of 1.96 is 0.025, by symmetry, the area to the left of negative 1.6 is also 0.025. So let's see if we can quickly look at, okay, so here we are looking at the z-score, and what we are looking for, the area to the right is a 0.025. Now, first and foremost, it is easier to go to the negative one, and area to the left is 0.025. Remember what we want. We want the area to be 0.025. So I'm using the symmetry on the left side and answer the question. So with that being the case, in the body, not the left column, not the top row, in the body, I'm looking for 0.025 or a number close to it. Okay, so let's see where we can find this. 0.025. Now let's do the reading. Negative 1.906. So if I'm reading the table, I would take the easy way out by using the symmetry. And I would read just 0.025, and it gives me negative 1.96. So I hope you can see the negative. Since I wanted a positive z-score, the area to the right was 0.025, then by symmetry, the answer would be positive 1.96. If I want to go with a positive z-score, then I can't look up 0.025. Instead, I got to look up 1 minus that. So I got to look up 0.975. So for a positive z-score, I'm looking for 1 minus 0.025. That means I'm looking for this area, 0.975. And now I do the reading. I see 1.9. I see 1.9. Up here, 0.06. There you have it. So that would be dealing with the table. And let's turn this on. Clear second variables. We move down to the third one, and we want the area. We decided we have to go with 1 minus 0.025. So 0.975, and it gives you the answer. 1.95996, and it continues for a number of decimals using technology and table. So let's quickly look at the last question.
Find the z-value such that the area under the standard normal distribution curve between 0 and the z-value is 0.2123. Find the 10th percentile.
We want the following. Probability of z being between 0 and some z-value we don't have. So this is what we are looking for. It's given as 0.2123. So that means here's the graph. From 0 to some number, the area is 0.2123. How do we look it up? One easy way, remember, if you go with the positive z-score, it goes all the way from negative infinity to the z-score. So you need to add 0.5. You need to add this area. And so you add 0.5. I hope everyone understands why. This is for the sake of reading. And you go to the table. In the body, you look for 0.7123. And according to this, the answer would be 0.56. Or you can use the technology as it was discussed, using inverse normal distribution. Now, in this case, what's going on when we say find P sub 10, or the 10th percentile? So that means the area to the left must be 0.1. If we were to graph something, the idea of this concept, this area is equal to 0.1, and this z-score is missing. That's the meaning of that. So if I'm trying to find this, number one, I'm going to do my graph. I'm going to do the graph so I understand what I'm looking for. So with that being the case, look at the table, look at the graph. We are interested in this portion being 0.01. I'm assuming everybody can look it up somehow using a table or technology to come up with this answer. Understand the area to the left is 10% or 0.1 because we are looking for P sub 10, the 10 percentile.